Hello everyone, welcome to the sixth lecture on operational amplifiers. In this lecture, we're going to see different types of popular op-amp circuits. So let's get started. The first circuit we have is voltage to current converter. Here you can see the circuit of voltage to current converter, which has inverting and non-inverting input, which is equivalent to 0 volts, and this way the load resistance is connected. So in this type of circuit, it is necessary to have a constant load current. When you give the constant input, then at the output you get the constant current. So this load current, which is not affected by any change in this load resistance, and this can be calculated by this formula: I out is equals to Vn by R, where Vn is the voltage across this input resistance. And as you know, as you can see here, the difference between these two voltages is approximately equals to 0 volts. Okay, so this V in input voltage, it will appear across this resistance R, which is connected to the inverting input. And the value of this load resistance, it will not affect the output current. So this type of circuit, if you have, then you can basically convert the voltage into the correct current, and easily you can calculate the value of current. Let's quickly read here. Because the differential input voltage VID equals to 0, Vin appears across the resistance R connected from the op-amp's inverting input to ground, and output current I out is calculated as by using this formula. So this is your voltage to current converter. Now next we have current to voltage converter. So this is the circuit for current to voltage converter, and in this you have the current source which is going in to the inverting terminal, and positive terminal or the non-inverting terminal is grounded. And then you have the feedback resistance here R, and then load resistance is connected. So similar to the previous type of converter, in this what you are doing, you are converting the input current into the output voltage. So here the current going in, as you know, by the ideal property of an op-amp, the current going into the inverting and the non-inverting side into the op-amp is approximately equals to 0. That means whatever the current you are sending here is going into this feedback resistance. Okay, so once you know the current flowing into this resistance, you can basically calculate the output voltage, because the voltage which will appear here is your output voltage. Okay, so the current will flow here, and then if you multiply with the resistance, then you can obtain the output voltage, which will be across this load. Okay, so the circuit is driven by a current source, since the inverting input of the op-amp is at a virtual ground, and all of the input current flows through the feedback resistance. So it's the same thing which I told you, that this is following the virtual ground. That means if this is grounded, then the same voltage will appear here. So the voltage here is going to be 0, and then no current will be going inside, and this whole current will pass through the resistance. So that's how you can calculate the output voltage, and this circuit is called your current to voltage converter. So I'll quickly go back to the previous circuit here. So in this particular circuit, we had a input voltage here, and we were calculating the output current, whereas here we have input as our current, and we are calculating the output voltage. Now next we have is the comparator. Comparator compares the two voltage levels which are given at the input side, and comparators, they basically work in the open loop mode, where the voltage gain which is obtained here will be equal to the open loop gain. So that's the same thing is written here. Voltage gain is equals to AVOL, and this circuit does not use any feedback resistor. So as you can see, there is no feedback resistance in this circuit, and this type of circuit, it can be used in analog to digital conversion, where you want to compare the voltage level, and then based on that you want to send the signal. So there you can use this type of comparator. And if your input voltage, for example, in this particular case, the inverting terminal is grounded and non-inverting terminal is given with some voltage level. So at the output, you will get the positive voltage, or you can say the maximum you can get is the positive saturation voltage. And saturation voltage is the same, which is the range here, the positive saturation range. And in case if this is grounded and this is given with some input voltage, then your output will go, the maximum it can go is in the negative saturation. So in this type of circuit, it has the propagation delay is really small, and they have fast rise and fall time, and slew rate of an comparator is higher compared to other type of op-amp. And their application, as I said before, that they are using analog to digital conversion. So they are mostly you will see in application where you have logic gates. So in this particular example, you can see how comparator can be used. We have inverting comparator here and a non-inverting comparator. So they both are the very same circuit. Only difference is that your reference in the case of inverting comparator is given at the non-inverting terminal. So and you're giving the input to the inverting terminal. So in inverting comparator, input is given to the inverting side, and reference voltage is given to the non-inverting side. And in non-inverting comparator, you give the input to the non-inverting side and reference signal to the negative terminal or the inverting terminal. So we are going to analyze like how the output waveform will look like for both of the circuits. So let's first see the non-inverting comparator. So this particular signal which you see is for non-inverting comparator, and the input signal is a triangular waveform, and which has some reference input voltage. So this is some reference voltage we have provided here. And so this circuit belongs to this particular waveform, and it says if your input voltage is greater than V reference voltage, then your output is going to be high. So as you can see here, so this is my reference voltage. So any voltage which goes above this point, that's my input. If the input goes above this point, and that's at that particular point, I'm going to get my output voltage. That's why you see this point, sorry, this waveform, and this has been obtained. You can see here, these are the reference point for this half cycle, and then for this cycle you have, these are the two reference point, and that's why your output waveform is turned on for this particular period of time. Whereas when you use the inverting comparator, where you give the input to the inverting side and reference provide to the positive side, so this is the input signal waveform. V reference is the reference voltage, and in this case your input voltage is less than the reference voltage. So as you can see here, input voltage is less than the reference voltage. In that case, your output is going to be low, which means inverting. So you can see this is the reference voltage. So anything below that you see, during that time your output will be turned on. So below this point we see this. So that's why we have output is turned on, and it is off whenever the signal goes above the reference point. So it is turned off, and again it is turned on because the signal is below this reference point, So this is turned on and then again off because now it is above the reference point. So that's how it works. And the third case could be when you have a lower threshold voltage and the higher threshold voltage is mentioned. Then if lower threshold voltage lies between the if the voltage lies between uh, lower threshold voltage and the higher threshold voltage, then your output will be high during that time. Okay. So if you implement this particular case, that particular comparator is basically called your window comparator, because you create a window, input window, and at the output you're getting the signal in that particular uh, threshold, lower threshold and the higher threshold. So this is an example of a window comparator, and this is the circuit of a window comparator where it uses two op-amps, Q1 and Q2 op-amp, and one side of the op-amp Q1 is connected to high voltage, or you can say this positive is connected to this particular voltage non-inverting side, and in the second op-amp the inverting side is connected to this VL, and the other terminal of the op-amp is connected to some input voltage. And the output, they both are connected through this load resistance, and then you have this V out which is coming out from here. Now let's consider three cases. First case is when your input voltage, which you are giving here, is less than load this VL. So this is VL and this is VH. So when input voltage is less than VL, then at that time your Q1, this Q1 op-amp is going to give high value, and Q2 is going to give low value. Why? Because your Vn is lower than VL in this case. So in this case your Q2 will be low and this will be high, but the total output is again is in this case is going to be 0, because this is a window comparator. So we have defined a window between VH and VL. When it's between them, then only it's going to be high. Now let's jump to this particular case when Vin is greater than VH. So when it is greater than VH, then Q1 is low and Q2 is high and output voltage is low. So anytime when your input voltage, whether it is less than VL or greater than VH, so whenever it is in this range, your output voltage is going to be low. But when it is within this range, which means when Vn is between VL and VH, the voltage value is under VH and VL. So VL would be the smallest value and VH will be the highest value of the voltage. So whenever it lies between this range, during that range only your output is going to be high, and your both the op-amp will be high and output voltage will be high. And the waveform is given here. As you can see, VH voltage has been defined here, VL voltage has been defined here. So during these two and then these 2 points, our output is going to be high. Okay. And on rest of the places, so this is the case. This case is that when your input voltage is greater than VH, and this case is when your input voltage is less than VL. Okay. So this is, in this case, VL is Vn is less than VL. In this case, Vn is greater than Vh. So in both the cases, the output will be low and it will be high during this line when you see when it is between VL and VH. So that's what you see here. We have this signal coming out. So that's the window comparator. Now, so far we have considered that the input which is coming to the comparator is ideal. So in that situation, we were getting the ideal output, but practically in your signal, you will have some distortion, you will have some noises, and your comparator should be good enough to basically avoid that noise or make a assumption that when it is supposed to be high or low, or when it should give the output signal. Okay, so for example, practically you will have signals like this. You will have some distortion superimposed on the signal. So in that case, if your V reference is like this, then you will get a signal like this. So this signal is basically affected due to noise, and this is not this will not be the accurate signal. So to do that, to make this circuit more efficient, what we do, we use the circuit called Schmitt trigger. So we use Schmitt trigger, which basically solve the problem by introducing the a threshold voltage, upper threshold limit and the lower threshold limit. So we'll see that. So here is your Schmitt trigger, and it is nothing but the comparator with hysteresis, which means it has two threshold voltages, upper threshold voltage and lower threshold voltage. And this symbol is a symbol of a Schmitt trigger op-amp. So when I say upper threshold and lower threshold voltage limit, that means, as you can see in this particular waveform, that this is my input signal going in here, and there is so much noise in this. And we define upper threshold and lower threshold limit. So if the signal catches here the upper threshold limit and any signal which is going around this limit, so this is my upper threshold voltage. So or if the signal goes into this, around this, then it will remain on until it goes to the lower threshold limit. Then only it will change, otherwise in between it will not change. So starting from here till here, you have you have the lower voltage signal till here. So once it reaches here, no matter you have the noises, still you will have the high signal here. So and that's applicable to this particular waveform. And as it goes down, once it reaches to the lower threshold limit, then the signal will fall down, and again it will go up once it reaches to this upper threshold limit. So that's our output waveform, and it will be much better compared to the previous comparator which we saw. And let's quickly move on to here. So this is the hysteresis curve which we get in the or you can say transfer characteristics of a Schmitt trigger, where this is your input voltage and this is your output voltage, and that's how basically your curve look like. So this limit is your in case of a non-inverting op-amp, this is going to be your upper threshold limit, and this is VH and VL you're giving. You remember at the input side you had VH and VL, and then this is going to be your lower threshold limit. So once it is at here, the output will be high, and this at here, output will be low. So now I will quickly move on to the main basic circuit of this Schmitt trigger. But if you want to study this particular circuit in detail, then I have provided a whole derivation of Schmitt trigger and how it works. You can go through the notes and it will tell you all this derivation for inverting and the non-inverting Schmitt trigger, as you can see here. So moving on to this, so a Schmitt trigger, this is the basic circuit which you will see in the notes, and this is the input voltage, and then you have this resistance R1 and R2, and output voltage, and the maximum range it can have is between plus minus saturation. And this Schmitt trigger is an op-amp comparator that uses positive feedback to eliminate the erratic operation caused by undesired noises. And this is the curve, transfer characteristic curve for Schmitt trigger. And this is this circuit which you see here may look a little bit different, but it's the same circuit which you saw in the previous slide. Only difference is that we are naming this one as R1 and R2, and it's going to the positive terminal. Um, and here also we have actually named R1 and R2, so it's pretty same. And then let's maybe quickly do this derivation here. So if V positive is greater than 0, then output voltage is going to be high, and if V positive is less than 0, then output going to be low. So what is V positive? Is the voltage which is basically here. So and then when you apply the KCL, so this KCL across this, and so at this node, KCL across this node, so this will give you V plus minus V in divided by R1, and plus V plus minus V out upon R2 is equals to 0, and that's what our KCL equation looks like. So when you simplify this and find out the equation for V plus, so for this particular voltage we get R2 by R1 plus R2 into V in plus R1 by R1 plus R2 into V out. So step 1, you will assume that output voltage is equals to VL. So the new V plus is going to be V1. So when this is VL, output voltage is VL, we are assuming that, then that will be your V1. Okay, so when this V1 is greater than 0, then output voltage is equals to VH. So, and then what we did, we assume that it is greater than 0, then this will be, this equation will become this. Okay, and then we can basically find out for V in input voltage, where input voltage will be greater than negative R1 by R2 into VL. So when this condition is met, then output voltage is going to be high. So that's your first step, and that's how you make your upper threshold limit based on this simple derivation by applying KCL and then finding out the upper threshold limit, and the same you will do for finding out the lower threshold limit. So when V2, so here this is VH, when your output voltage is VH, that means your V2, that means your V2, so this is now V2 will be less than 0. So it will be less than 0. In that case, your Vin will be less than minus R1 by R2 into VH. So output voltage is going to VL. So if it is overwhelming right now, you can just pause the video and quickly go through this derivation and try to solve on your own, and you will see how we create the upper threshold limit and the lower threshold limit. So if you let's look at this particular transfer characteristic, and ultimately you should know that for upper threshold limit, the formula is basically equals to negative R1 by R2 into VL, and for lower threshold limit it is negative R1 by R2 into VH. And that's ultimately was our goal to drive through that derivation which you saw. So that's your Schmidt trigger, and application, it can be used in wave shaping, analog to digital conversion, in level comparator it can be used in multi-vibrator, in oscillators, as a positive feedback circuit it can be used. So that was the Schmidt trigger, and now the next we have is the precision half wave rectifier. Precision half wave rectifier is used to detect a very low level of signals, and this is the basic circuit you see here, where you have an op-amp connected to the diode, and the output of the diode is basically fed back to the inverting terminal, and here you have this load connected here, so you get signals something like this. So that will create your half wave rectified output. And this circuit is capable of rectifying signals having peak values in the millivolts region. Now I'm going to show you another circuit which utilizes the capacitor and which is connected across this load resistance. And in that case, so here you can see this is the circuit precision peak detector, and you have some input voltage going in here, and this is the same diode and the load resistance, and then you have this capacitor over here. And then what will happen when your input signal, when it is positive, then this diode will be forward biased, and then what will happen in that case, your capacitor will start charging up at the output of the peak positive value of the input voltage signal. And then when your input voltage, when it is less than your this VE, this voltage, this V, then what will happen? Your capacitor will basically discharges through this load resistance, and in that case, your discharging time constant will be given by this. So this is going to be your RLC, discharging constant, discharge time constant. And where T is the time period of the input waveform. And to obtain the negative output voltage, you just reverse the diode. So that's your precision peak detector. And that's all for today. And if you want to see the derivation, you could go and see the lecture notes. So thank you so much for watching this lecture.